All right, welcome to my talk. Today I'm going to be talking about how we can leverage macOS's networking frameworks to heuristically detect malware. So we had a great talk this morning from Brandon. He talked about using endpoint security. Endpoint security is amazing. Somewhat complementary to that is some of the frameworks I'm going to be talking today that allow us to see strange network activity to detect malware. So what will we learn today? We're going to learn how we can use macOS's networking frameworks to heuristically detect malware, key point directly on the host. So we have a lot to go through, so I'm going to jam through this quickly-ish, so forgive me for that. We're going to start by looking at some Mac malware samples to show how Mac malware utilizes the network. We're then going to talk about how to build a tool to enumerate the network state, kind of a snapshot of network activity. We're then going to talk about how to build a network monitor, specifically one that will capture DNS requests. And then finally, once we detect network activity, how do we attribute it back to a process and determine if that process is something legitimate, user's browser, or some new malware. Now, the idea, and this is not necessarily the most novel idea ever, is that we should be able to detect malware via unauthorized network activity. And this is because the vast majority of malware is going to use the network. If you were in my training yesterday, I talked about many different infection vectors that malware could use to get on your system. Zero-day exploits, Jaron mentioned cracked applications, we saw browser pop-ups, a host of things. Those are all difficult to detect because there's so many of them. Well, once the malware gets onto the system, it's going to do a few common things. One of those is access the network, maybe download additional payloads, check into a remote command and control server, exfiltrate files. So if we can detect this unauthorized network activity, point number 2, in theory, we should be able to generically detect a wide range, if not all, or at least most Mac malware. Now, one thing I want to point out is the way this is normally done is by taking a dedicated hardware device and plugging it into your network, something like a hardware firewall, network monitoring capability. And that's all well and good. It works, but there's a few downsides to that approach, downsides that I think should really make us reconsider this approach and perhaps focus on host-based network monitoring, which is running the detection directly on the endpoint host, for example, on a Mac. So the biggest downside, I think, is a lot of these network appliances have security vulnerabilities that advanced adversaries are both finding and exploiting, which is disheartening, or at least ironic to say the least, because these are supposed to secure your network, and if the Chinese are coming along and popping them to get into the enterprise, that's super unfortunate. So on the other hand, host-based network monitoring requires no extra hardware. It also happens pre-encryption, so if you're doing full packet capture, you don't have to man in the middle and decrypt traffic, which is really nice. And also then, most important is that it allows you to identify the responsible process. So Brandon talked about this morning when an endpoint security event occurs, tying that back to the process that originally triggered that. Well, we want to do the same thing for network activity. If you're running a network appliance that's somewhere else on the network, you're not going to be able to say that, okay, this DNS request or this connection is tied to a malicious process. But on the host, we can actually determine who is responsible for the network activity and then figure out if it's suspicious or not. So the idea is pretty simple, but unfortunately, until recently on macOS, it was rather challenging to do, to say the least. So not to pick on Apple too much, but a lot of their code was originally rather buggy. So I, for example, would release this great free open source firewall that used network extension as Apple recommended. Users would run it, the box would panic. Everyone would yell at me. I look into it. There's a kernel bug in Apple's code. Not ideal. Luckily, Apple has, moved on and this is now fixed. So that's good. But we'll see there's other challenges. For example, some of the frameworks we want to use are private, which means we have to reverse engineer them. They're not documented. And some of the documentation that Apple provides is rather lacking. Also, Apple actually originally neutered their networking extension framework to begin with, which is really, in my opinion, very problematic. So long story short, we used to do everything in the kernel. Apple said, no, that's bad. You got to do this in user mode. But we will provide you with a framework that will, for example, route all traffic to any clients that subscribe to this user mode framework. Okay, awesome. Sounds great. I don't like writing kernel mode code anyways. Well, that was all well and good until we figured out that Apple had created an exclusion list they didn't tell anyone about, with a very long list of system processes and applications that would be exempt, meaning their traffic would not be routed through this framework. That's very problematic if you're trying to build a firewall if half the traffic on the system is not being routed through it. And to illustrate this, I found a very trivial way to exploit, or rather leverage, some of these trusted or excluded items to generate network activity on my behalf. So I was able then to create a proof of concept malware that could access the network, and even if there was a firewall installed, it wouldn't see its traffic. It was blind. Reported this to Apple. They were like, yeah, this is kind of by design. Talked to some of my friends in the media. They kind of brought more attention to it, let's just say, and luckily Apple decided that, yeah, this was a bad idea. And so another lesson, if you ever want to change Apple's opinion on something, the media is the way to do it. And I don't know if that's a good thing, but this is the reality, and so, take that for what it's worth. Okay, so now let's look at some recent Mac malware samples to see how they access the network, because if we're writing network monitoring tools, we need to have that baseline understanding so we know what to look for. So first off, we have dummy. I named this malware dummy because it's very simple. But maybe that's an unfair name because, well, it actually provides a remote adversary the ability to execute any command on an infected system. So it's a standard reverse shell. You can see it's a bash script that was persisted. And in the bash script, they would execute some Python code that would essentially connect out to a remote server, redirect standard in, out, and error, and then spawn an interactive shell tied to that socket. So again, this is how you create a remote shell, reverse shell, that would allow a remote adversary to run commands that would then be executed on the shell of the local host. Another sample is IP Storm. IP Storm is interesting. It's cross-platform, also ran on macOS. And as we can see on the slide, the researchers who analyzed it showed that it would actually utilize the network to attempt to spread autonomously to other systems, which is interesting. We don't see a lot of Mac malware, or malware in general, with the ability to do that. They basically try to brute force SSH sessions. It also had the ability for a remote shell as well. So access the network in several ways, giving us opportunities to perhaps detect it. Next up, we have GoRat. GoRat is fairly standard, albeit fully featured macOS backdoor. So here's some of the commands that it supported: upload, download, screenshot, etc., etc. But as we can see, it did support a few commands specific to network activity. So you could tell it, for example, to port scan another host. It's kind of a neat feature. You could also set up a proxy so that it could talk to another infected system, perhaps that was internal to the network that couldn't directly talk out to the internet. So again, lots of opportunities to perhaps detect this infection by detecting unauthorized network traffic. We had some talks today that mentioned supply chain attacks. The 3CX one of the most recent, most prolific ones. And as Sal mentioned, there was a component that infected macOS, or targeted macOS users as well. Supply chains are notoriously difficult to detect, and the 3CX is an example of this because what the attackers did was infected the 3CX's official build servers, surreptitiously modified the installer, added some malicious code, signed it with the code signing certificate belonging to 3CX, and then worse, sent it to Apple, who inadvertently notarized this. So now anytime the users of 3CX updated their software, even if they were going to the legitimate website, they would get a signed notarized package application that everything looked good, but would contain malware. So how are we supposed to detect this, right? This is very, very difficult. Well, it turns out it was originally detected by somebody noticing suspicious DNS traffic. They basically saw that the 3CX application was now talking to another unrelated endpoint that was suspicious. So I think this points out that network detection can provide a great way even to thwart advanced attacks like 3CX. And the last one I want to mention is an iOS attack. Yes, this talk is focused on macOS detections, but a lot of the concepts apply to iOS as well. For example, the network extension framework also exists on iOS. And I think this also drives home the fact that what a powerful approach to malware detection we can by using network monitoring. So in this case, the long story short, Kaspersky researchers were targeted by a very advanced piece of iOS malware. It infected their iOS devices and remained undetected for 4 years. That is insane. Kaspersky is one of the world's premier security companies. Why were they targeted? Well, you can probably guess, a separate story there. But the fact that they were not able to uncover this for essentially half a decade is insane. How were they eventually able to figure this out? Network traffic. And this also is one of the only reasons or only ways I think you can effectively detect advanced attacks on iOS, because you really can't run a lot of security software directly on the device. Okay, so hopefully I've shown you that a lot of Mac malware uses the network, and if we can detect its unauthorized access to the network, we should in theory be able to detect even the most sophisticated supply chain attacks, iOS malware, and everything in between. So now let's talk about how to do this programmatically, starting by looking at code that will give you a nice snapshot of network activity using the private network statistics framework. So as I mentioned, the goal is to provide a global snapshot of all network activity. I mean, connections, listening sockets, et cetera, et cetera. Now, there's this utility built into macOS that I was not originally aware of, and it's called nettop. If you run nettop, it gives you a nice global snapshot of network activity. So I was like, cool. Fortunately, it's closed sourced, and I was like, how do we figure out how to use that? Well, if you use OTool, we can see the dynamic libraries that this tool depends on. And I've highlighted the one that's most relevant. It's the Network Statistics Framework, and we can see it's in the private framework directory. This means it's an undocumented framework. Apple doesn't really want you to use it, but I myself and Jonathan Levin did some reverse engineering effort on it, and it turns out, well, this is exactly how the nettop utility gets its information. So once I finished reverse engineering the framework, I could talk to its APIs. There's nothing preventing you from using a private framework. It's just not documented, so you have to understand how to talk to it. But once you can, you're allowed to use it. So what I did was I created a tool called Netiquette that is built atop this private API framework. And as we can see, it provides us now with a nice snapshot of network activity. Also, since it's a UI, you can filter based on names, states. You can, for example, say ignore all or hide all Apple processes, which is useful if you want to just see what third-party applications or perhaps malware is accessing the network. So here's the code to do it. I'm not really going to spend too much time walking through source code. That's never a fun thing, but these will be in the slides that will be shared along with all the other slides from today. And so if you're interested, see this more as like a resource you can go back to. But what we do in a nutshell is we create a network statistics manager that's implemented in this private network statistics framework. We tell it we're interested in all TCP and UDP traffic, and then we initiate a query which will tell it to start enumerating the network state. And for each network entity, which is something like a network connection or a listening socket, we will get a callback with a dictionary that contains all the information about the connection, which is exactly what we want. We can then link in the private network statistics framework, compile it, and then run it. And as you can see on the slide, it's kind of hard to read. That's by design. The takeaway is just how much information we get. This is for one single connection, in this case, a connection that GitHub Desktop is responsible for. So the most important thing we get, I think, is the responsible process. So we say, who's doing this? We also get all the information about the connection, the remote host, destination, port, et cetera, et cetera. And we also get the transmitted bytes up and down, giving us statistics. I guess this is why it's called the Network Statistics Framework, which is really interesting because that allows you to also develop rules or heuristics, perhaps detecting software that's exfiltrating large amount of data, which is, could be something that's exfiltrating, like one of the stealers that was talked about before. Now, this is great. Snapshots are awesome. They're good to baseline the system and see if anything's strange that's happening. But there's one downside, which is you can only enumerate current activity. So on the slide, we have some examples of malware that's perhaps either going to sleep or have time intervals between connecting out. Obviously, if you perform a snapshot while the malware is not actively accessing the network, you're not going to see anything. So the question then becomes, can we develop something that's a little more comprehensive? So what I want to talk about next is building a network monitor that continually monitors the network. And in this case, we'll focus on DNS traffic. The idea is that by monitoring DNS requests, in theory, we should be able to efficiently detect malware's name resolution. So I'm sure many of you know how DNS works. The idea is it basically maps a domain to an IP address. Like computers don't understand domains. Those domains, google.com, those were created for humans. So what happens is when malware wants to talk to its command and control server, say it's like msmessageboxes.com, which is one of the ones that the 3CX attackers set up, well, the malware first has to resolve the IP address associated with that, which causes a DNS request to be made. So the idea is if we can monitor DNS requests and tie them back to the responsible process, we should be able to detect a large amount of malware without having to monitor all network activity. So the way you build a DNS monitor or any network monitor on macOS is by using the network extension framework, network extension. And I did knock on Apple a little bit earlier. The network extension framework now is pretty solid and well documented, which is really nice. And if you read the documentation, you can see it allows you to do all sorts of really cool things, including monitoring DNS activity by something they refer to as a DNS proxy. There's also a WWC video that describes it in detail. Highly recommend looking at that as well. So how do we create a DNS monitor? So I looked at the network extension documentation, and I noticed that there was this class called NEDNS Proxy Manager, and it says this allows your application to intercept all DNS traffic generated on a device. And I was like, perfect, this is exactly what I need. Now, I'm a little lazy. Like if someone else has already done this, I don't want to reinvent this. So I hopped on Google and Googled it, and other than Apple's documentation, there was one hit, and it was someone on Stack Overflow being like, yo, how do we do this? And so I was like, bummer, but also I saw this as, okay, this is a decent learning opportunity. And if I create an open source DNS monitor using this, that should be useful to other people as well. So the tool is very creatively called DNS Monitor, maybe not my best work. And it's as its name implies, a host-based DNS monitor that also has blocking capabilities. Free, open source, pop over to Objective-C's GitHub, download the source code. But we can see that when it's running, if I try to resolve any DNS name domain, for example, via NSLOOKUP, the DNS monitor will detect that and log it to standard out. Now, unfortunately, there's many prerequisites to building your own network extension that Apple leverages on it. First, you have to have the necessary entitlements, meaning you need a paid developer account. You also have to build your application in a very specific way, putting the component that does the monitoring, which is the actual extension, within an application bundle, specifically within its contents library system extension folder. Then you have to sign and notarize it. So that's all well and good, but now you run into the next set of prerequisites, which are when the user wants to run your tool. So some of you might say, okay, cool, DNS monitor, Patrick, sounds neat. I want to give this a whirl. You pop over to Objective-C.com, get ready to start clicking. First, you're going to have to click on the allow button when Safari says, are you okay downloading something from Objective-C? Okay, well and good. Then when you go to launch it, Gatekeeper is going to hop in the way and say, okay, even this is signed and notarized. It's from the internet. You have to approve it. Okay, you click OK. It's then going to say, wait a minute, this application, signed and notarized, which you've just approved, contains a system extension. You have to allow that. So you click Open System Preferences, click Allow, Authenticate, and then there's one final prompt saying, okay, the system extension that you just approved from this notarized signed application that you also approved wants to access or utilize the network. And I make this joke that, I don't know if y'all remember, but Windows Vista got a lot of heat for all its prompts. And at that time, Apple made a very creative advertisement basically pointing out the flaws, which at that time I thought was genius. However, it's kind of like we come full circle and Apple is now Vista. So I actually went back and found this advertisement, which is Apple knocking on Vista. But as we'll see, I think Apple's become what it dislikes. So I'm turning the volume on this. It's also subtitled, but again, this is an Apple commercial, very creative.
Hello, I'm a Mac. Mac is issued a salutation, cancel or allow.
Allow, and I'm a PC.
You're returning Mac salutation, cancel or allow?
Allow.
Okay, what? gives. Mac is asking a question. Cancel or allow?
Allow. He's part of Vista, my new operating system. PCs have a lot of security problems, so he asked me to authorize pretty much anything I do.
You're pointing out Vista's flaws. Cancel or allow?
Allow. I could turn him off, but then he wouldn't give me any warnings at all, and that would defeat the purpose, so.
You are coming to a sad realization. Cancel or allow?
Allow.
So if you were counting, there was 5 allows in the advertisement. To install and run a signed notarized network extension, there's 6. So not ideal. Now, I will caveat that to kind of get around this, this should be deployed in a managed environment. So in enterprises, it's not quite problematic, but I really think Apple could do a better job. Talking with them, they basically say the problem is there are autonomous groups that are responsible for each prompt, and none of them really talk to each other, and there's not a lot of state going through. So even if you allow one component, the next piece doesn't know that, and blah. Anyways, maybe Apple will improve this in macOS 15.
Oh, they're going to implement Heuristics.
Oh, even better. All right, so I briefly want to mention how we can implement a DNS monitor. Again, this could be a whole talk unto itself. If you're interested, I'd recommend looking at the source code for DNS monitor. But I do want to mention some of the core methods because they are pretty important. So the idea is you implement what is known as delegate methods. Delegate methods are methods that if you implement, the framework or the operating system will automatically invoke them when some event happens. So when you're building a network extension, you should implement the start proxy and stop proxy completion handler methods. These will be invoked when your DNS monitor is started and stopped. Really don't have to do too much there. But the most important one is this handle new flow method. And if you implement this, anytime a new flow occurs, flow is Apple's term for basically a network connection, in this case, a DNS connection, this method will get automatically invoked, which is perfect. It gives us the ability to look at the DNS request to see if something we should allow or deny. Now, if you remember the name of the class, right? It was something like any DNS proxy. Basically, what we're building is actually a proxy. And the idea is that any application that makes any DNS request, that request will be routed through our network extension on the host. But that means we are responsible then to go out and complete the DNS request. So there's many steps we have to do. We have to open the local flow, read the datagrams to get the DNS request, open the remote endpoint to a DNS server, and then send the datagram out. When the response comes back, instead of being routed directly through to the application or program who made that initial request, it actually comes back through our proxy. Again, this is good. It gives us the opportunity to examine that request, but then also means we are responsible to passing it on to that application. Now, you might be thinking, okay, great, we're getting DNS packets. How do we parse this? And I first said, I'm going to parse DNS packets myself. Bad idea. Steve laughs. He knows. Turns out, though, there is a library that does this for you, which is good. You should not be parsing network packets yourself. It's very complicated, error-prone, and if you mess it up, you might introduce security vulnerabilities into the system. So at this point, we have our proxy. We're getting raw DNS requests and raw DNS responses. We can use Apple's libresolve library to basically give it the raw packet. It will nicely parse it out for us. Okay, beginning of the talk, I said, in my opinion, the best reason or the main reason you should be doing host-based network monitoring is because it allows you to identify the process responsible for making that request, which then allows us to see if that's malware or not. But I haven't told you how to do that. Well, in that handle new flow method that's invoked anytime there's a new network request, one of the pieces you get is a flow object that has what is known as an audit token for the responsible process. An audit token is just a unique way to identify a process. It's a more secure alternative to a PID or a process ID. So there's code for on the slide. You can see that once we get this audit token that's passed to us by the framework, we can get its path, we can get code signing information, we can get all the information we want about the responsible process. So if we compile and run this, we can see some output from DNS Monitor, the proxy application we've implemented. And we can see now if we run an infected instance of the 3CX application, we can identify both that it's making a request and also attribute it back to the application, in this case, 3CX. Now I thought, okay, great, we can monitor these events. Let's start blocking them. So we can block it at two different ways. both when the request is going out, we can look at the domain and say, is this a domain we don't like or we don't trust? Or when the response comes back and we have an IP address, right? So we're resolving a domain to an IP address. It's also good to be able to block the IP address, the response is coming back in, because perhaps the attacker is using the same infrastructure and just mapping it to different domains. So here's the code that does the blocking on the outgoing response. We basically parse the DNS packet and look for the questions. That's the domains that are being resolved. And if we don't like any of them, we can just close out the connection, which basically means that the resolution will fail. Here's an example. I added Google to my block list, try to resolve it. The DNS monitor detects it, sees it's on the block list, closes out the connection, and the resolution fails because it times out. As I mentioned, we also might want to examine the answer that comes back. Maybe we have a list of IP addresses on a block list. Basically the same thing. However, when we get the DNS response, we look at the answers, which are the IP addresses that were resolved. And same thing, we can then just close out the flow. Turns out we can also block it by creating what is known as an NX domain packet. This is basically telling the application or who is trying to resolve the DNS request or domain that it doesn't exist. So this is just an alternate way to essentially block a domain, perhaps the more recommended way. We basically just make a copy of the packet, set some header flags, and basically say, sorry, the domain you were trying to resolve just doesn't exist. And again, this will cause the resolution to fail, essentially blocking it. The last thing DNS Monitor does is also has a cache. So it stores a list of all the IP addresses and domains that they map to. And so you can send it a signal and it will print out the cache. Now there's one shortcoming. I always like to point out shortcomings in my tools, and that is if malware is directly connecting to an IP address, this doesn't require any DNS traffic, so nothing will be routed through our proxy. The solution, of course, is to create a fully featured network monitor. The network extension library framework allows you to do that as well. But this is kind of a rare case, and perhaps if you're combining your DNS monitor with a snapshot-based approach, you would detect once the connection is established, even if it's not using any DNS traffic. Okay, I want to wrap this up by talking about heuristics. At this point, we have the ability to effectively see all network activity, either via a snapshot or when a DNS request is made. And that's all well and good. That's an important prerequisite. But how do we determine if the process that is responsible for that is malware or not, right? Is it user's browser or is it something suspicious? So the question really is, how do we classify the responsible process as benign or malicious? There's two main ways. You can either examine the responsible process, which we will talk about shortly, looking for characteristics that might be indicative that it's malicious, or you can look at the network information. And there are lots of talks. There's books on, okay, given a request to a certain domain or a certain protocol, that's something that's likely malicious. So I'm not going to cover that. Some examples are, if you see a listening socket that's bound to an external interface, that might be shady. If you see something connected to a known command and control server, probably shady. Family protocol statistics, something beaconing every night at midnight and sending up gigs of data, that could be strange. So let's now focus, though, on, since we have the responsible process, and as I mentioned, that's one of the main benefits of using a host-based networking approach, how do we determine that it's malware or not? So here's a few ideas. There's many ideas, but I wanted to mention some of the ones that are my favorite. So first off, if something is not a platform binary, meaning it's not part of macOS, and is also not notarized, that's something that should be closely examined. Because although Apple does inadvertently occasionally notarize malware, for example, in the 3CX attack, that's actually very rare. And the other takeaway is that most malware isn't notarized. Because to notarize something, you have to send it to Apple. Most malware authors don't want to send their malware to Apple because Apple will likely detect its malware and revoke its certificate right then and there. Here's some more code. Not really going to go through it all, but the idea is you can basically use the code signing APIs on the operating system to, given a path or a process ID or an audit token to a process, ask, is this notarized or not? And the API will say yes. Full code, one of my other tools, block, has a notarized mode setting, blocks anything that's not notarized. A lot of the talks today noted that a lot of malware persists. So if you see something accessing the network, it might be wise saying, is this persistent or not? If I see something that I don't recognize, something new that's accessing the network that is also persistent, it doesn't necessarily mean it's malware, but it's something I'm going to take a very close look at. On recent versions of macOS, Apple introduced what is known as background task management. It's a subsystem that governs the majority of persistent items, login items, launch agents, and launch daemons. The good news is there is now a database that contains all these persistent items. So once something accesses the network, in theory, I can query this database and say, is this item persistent, meaning it's in this database. Unfortunately, this database is undocumented and uses undocumented serialized objects to store that. I reverse engineered that though and figured out the format of that and wrote a free open source tool called dumpbtm that provides information about that. So for example, here we can see the entry for dummy. We can see it's a persistent item. So using this library, I can now answer the question, is process X, which is accessing the network, persistent or not? Finally, process hierarchies are always great to look at. Jaren is the process hierarchy guru because on macOS, it turns out it's way more complex than simply looking at PPID or the process's parent. I'm not going to go into all the details. Hit up Jaren. He also gave an OBTS talk about that if you're interested. But end result is we can now build pretty comprehensive process hierarchies, which is good. So back to dummy, recall that it used Python to connect or to create a reverse shell. That's kind of difficult to detect if we just look at Python because Python is a legitimate component of the operating system. So it's going to be notarized or specifically belongs to macOS. So there's nothing shady about Python per se. What is shady is who spawned it. And if we looked at the process hierarchy, we can see that it's spawned persistently by bash and tied back to a persistent script. So that's like very many red flags. So looking at the process hierarchy is also a good idea. Okay, so let's wrap this up. Main takeaway is malware uses the network. And macOS does now provide us the capabilities to build comprehensive monitoring tools that we can leverage to generically detect malware. So that is a wrap. Do I have time for a question? Sure. Questions, one or two? Questions? Yes, in the back. And where's the, okay. Ready? Okay. We got to make it through the conference without, taking anyone's head off.
I'm curious if I don't use Mac's DNS resolver and I figure out another way to resolve it, like how would that show up? Like would it bypass this? And that's, I mean, I've kind of seen this before where Google
Sure.
Chrome does this,
Yeah.
and then there's no evidence that they went to a website or something like that. So
yeah, that's a great question. I don't have a comprehensive answer for that. My basic testing has shown that even Chrome's traffic will be routed through this. My guess is what Apple is doing is DNS requests that use standard APIs are routed through this DNS proxy. But if you're doing something lower level or something more manually, that would sidestep it. I think another example would be DNS over HTTP or what it's DOT or something. Or yeah, I think that traffic is not routed through that because this is really kind of like traditional DNS traffic over port 53. I haven't seen any malware that does that more advanced stuff. It's probably out there. So that's, I would say, another reason why having a fully featured network monitor is maybe a good idea. There's some additional complexity involved with that. And also then you're seeing all network activity. So there's more to process. But the upside to that is that would show you any network activity and still allow you to tie it back to the responsible process. And then if you detect it's port 53 traffic that's not like kind of a standard DNS resolution, that's a red flag unto itself. Great question, though. Yes?
I block an DNS over HTTPS for this exact reason, so I can actually see all of the DNS requests. I also use my own network to do DNS, so I can actually also see it from the outside.
Yeah, from the other side.
Just in case there's kernel bypassing.
Yeah. That's another good point, too. If something's going on in the kernel, you're not going to see any of this because this is running in user mode. And I think that's a general statement towards security tools in general. But that's interesting. I didn't know you could turn off DOT TDOH. What is this?
Yeah,
DNS over
HTTP,
HTTPS.
yeah, DOH.
So that might be a nice feature if you implemented this in a security tool, would be to disable that to essentially funnel or force all DNS traffic through your tool specifically. I think we have time for one more question. Corey, go for it.
Would it still work even if you say use a VPN? Would it still catch it?
That's a great question. I don't know. I would have to test that.
It won't.
It would?
It won't.
Oh, it won't. Okay. Yeah. So I think really it's limited to kind of like standard DNS traffic. And if you're routing it through a VPN or doing DNS over HTTP, it's gonna bypass. So in that case, you would have to either do fully featured network monitor, or if a VPN is in use, I think for maybe malware detection, that's not maybe that interesting, because I don't know if the malware would be routing its comms over the VPN, or if it was, like, maybe there would be some other things you would have to do.
Because I was kind of thinking of when like his talk,
Yeah.
that it was going through technically.
And I think that's when, like, the snapshot-based approach is neat too, because you would see, process X, you get more information that could then maybe give that. But I think that's important to note. And I think, again, it's like no security tool is ever going to be a panacea, silver bullet. So it's always kind of good to do kind of more comprehensive stuff. So